this video, we will determine the variance of the method of moments estimator of a uniform distribution. Let's get started. You are given the following. A random variable x is uniformly distributed on the interval 0 to theta. Theta is unknown. For a random sample of size n, an estimate of theta is given by 2 over n multiplied by the sum of xi's. Calculate the variance of the estimator. For this problem, I decided to derive the variance of a uniform distribution. Really appreciate it if you guys could comment below and let me know if this is getting too in the weeds or if you find this interesting, because this is definitely pushing the limits of information you need for the exam. But I thought it would be fun to derive it. In a more applied setting, you really probably should just have the variance of the uniform memorized, or if you don't have this memorized, just know that a uniform is a beta distribution with inputs of 1 and 1 for those two parameters. And then you can just use the formula sheet. So one of those two things is how you should actually go about this problem in an exam setting, but thought it would be interesting potentially to actually derive the variance, because honestly the 12 has been throwing me off forever, so I kind of wanted to get to the bottom of that. So yeah, comment below if you find this upcoming section helpful, and if not, I can kind of trim the fat in future videos. So first off, need to know that the variance of x is the expected value of x squared minus the expected value of x squared, just by definition, and that the way we get that is integrating in the domain of your distribution the probability of all the values corresponding to that x. So here, when you have a uniform distribution, every individual value has equal likelihood, and that is going to be 1 over b minus a. And if you have a width of 1 and a height of 1, width times height is going to be the total area, and you need that to equal 1 because it's a PDF. And so that's why the height of that rectangle has to equal 1 over the width, so that way the total area under the curve is just 1. So that's why the probability is constant, just 1 over b minus a. And we're multiplying by x squared here because we want the expected value of x squared. Then we subtract off the same thing, just minus that squared term. So it's the integral of x multiplied by the PDF, and then that overall quantity is going to be squared. We then take the antiderivative, so put it to the third power and then divide by 3, and then likewise for the right section, but for a value of 2. And we're going to integrate from a to b. Then, let's see, just plugging those values in, so it's going to be the b first, and then you subtract off the lower limit a, doing that for both. Going to the next section, let's see what we have here. And then since they have the same denominator in each on the left and then the same denominator on the right, we can combine them. So we're just putting them both in the numerator. And let's see what I do next here. So then on the right side, I decide to, at this moment, square. So 1 over 2 squared is 1 over 4, and then both the numerator and the denominator, you can just square those terms. So at this point, we want to be able to put everything in the same fraction. So to get a common denominator between the left and right side of this calculation, we actually need to get a 12 b minus a squared in the denominator. So we just multiply by 3 over 3 on the right side, and on the left side a 4 times b minus a, and then we get a common denominator between them. So that's, showing that they have a common denominator here, and then putting them together here. The final step is then to expand all this out. I'd also say at this point, if you've done a lot of polynomial expansion, maybe you're able to kind of just look at this and know where this is going. I feel like back in high school when you were learning polynomial expansions, you would be a lot better at picking this out a lot sooner, but I had to write all this math out and tripped up a few times. So let's see. Here we're just distributing 4b to both and then negative 4a to both. That's how we get this mess. And then we need to square this. So you're going to get b to the fourth minus 2a squared b squared plus a to the fourth, all of that multiplied by 3. And that's how we're getting this. And yeah, okay, so we have that. Let's see what we do next. I think here I'm just rearranging. Might have just accidentally copied and pasted that twice. So going to the next, we're going to combine like terms. So here we have 4b to the fourth, and here we have a negative 3b to the fourth. So that just becomes b to the fourth. And then likewise for the a term, there is a to the fourth and a negative 3a to the fourth. And then we're just left with this in the numerator. And then let's see what we got next. Here I am just reordering just to make this next step a bit more apparent. So b minus a to the fourth is equivalent to this expansion. So that's what I was referring to by, maybe you could have seen this coming or anticipated this, but this is just the expansion of b minus a to the fourth in the numerator. And then now that we have that in the numerator, we see like terms cancel. And so all we're left with in the numerator is b minus a to the second, and then that 12 stays in that denominator. And that's how you derive the variance of a uniform. So that's that, and that's 5 minutes you're not going to get back, so I apologize. So now moving on, the second thing you need to know for this problem, we'll eventually get there, I promise, is the variance of x plus y is just the variance of x plus the variance of y given they're independent. So you need to know you can break that out for variance calculations, and in the problem that's going to be in the terms of the fact that individual samples of x are going to be IID, so they're independent draws from the same distribution. The final thing you need to know is when you pull out a constant from a variance calculation, you square that term. So again, similar fashion to the uniform variance calculation. Let me know if this is more detailed than you want, but thought I'd derive this since it's kind of a similar setup. So here we're just doing that expected value of x squared minus the expected value of x squared. But in this case, x is a times x, because that's what we're interested in. And then what we can do is pull out the a squared because it's just a constant, and it goes here. And then on the right side, we can pull out the constant, and then that constant gets squared. So that is also pulled out. And then finally, we have like terms of a squareds, pull that out, and all that is left behind is actually just the calculation for the variance of x. So that's why when you have an a, just a constant, and you pull it out, you have to square that term. All right, so now we can get into the actual problem. So let's see what we got here. First off, just something to note, not important for this specific problem, is this is a method of moments estimation, and that's because we're using the expectation of x to create our parameter estimate, or some function of that estimate. So just taking the average of x and then multiplying it by 2 is the estimator. So it's a function of the sample mean. So we're going to determine this variance, just writing that out of what our estimator is. We then break this up, so sigma, I just chose to actually kind of denote it by addition signs, so we can more clearly see this second bullet point we discussed earlier, that we can break them apart. And that's because each individual sample is IID, and so we can break the variance calculations up. Then applying our constant removal and squaring that term, we get these 4 over n squared constants pulled out. So again, 2 over n is a constant. We can pull it out if we square it, and that occurs for all of these calculations. Furthermore, we know that the variance of x1 is equal to the variance of x2 because they're all samples from the same target distribution. So really this is just the variance of x, and it's 4 over n squared times the variance of x plus 4 over n squared times the variance of x all the way up until n times. And so we can actually simplify this to be 4 over n squared variance of x multiplied by n. The n's cancel, and then all we're left with is 4 over n times the variance of x. So the final piece of the puzzle is just knowing that for a uniform distribution, which is what x is, the variance is theta minus the minimum, which is just 0 squared, divided by 12, so theta squared over 12. Plugging that in to what we have here for the variance of our estimator, we get 4 over n times theta squared over 12 is just equal to theta squared over 3n. Scrolling up. I forgot to color code it, but the answer is E. Thank you for watching. Please comment below if you enjoy these types of videos. And until next time, have a good one. Bye.